Welcome to this Nexus tutorial.
We will cover the creation of a digital buck controller from scratch.
The power electronics will be running in Plecs, and the controller will be an application written in C. They will be running in independent but synchronized processes, showcasing Nexus capabilities. They will be sharing signals, as the measurements generated in the power stage, and the duty cycle that will control the switch.
Let's start by downloading the examples from the public GitHub repository and making a copy of the template project in our working directory. Inside it, we will find a folder named Shared, which contains the header interface for the simulation units. Let's edit the header file, adding our measurement and control signals. First of all, the simulation ID has to be written with a unique name. Next, we will write the signals in separate structures for clarity. This header defines the map of data that will be shared across the simulation. Now we are ready to create the simulation units. Let's get started with the buck converter power stage. We will be using Plecs, but the process is similar for other applications. So let's create a basic buck circuit, including measurement devices for output voltage and inductor current and labels for them and the PWM signal. We will also create a PWM generator inside this circuit, to test that it works as expected before connecting the digital controller. Now let's set the values in the components. We will be simulating a 5 volts power supply, with a 1 mH inductor. Let's make the capacitor larger so we can observe the overshoot, and let a 1 ohm resistor as the load. With a 50% duty cycle at the PWM, we should see 2.5 volts at the output. The switching frequency will be 100 kHz. Let's finally add a scope so we can see what's going on. We will plot the PWM, output voltage, inductor or output current, and duty cycle.
And let's save the circuit in the project folder inside units. We will copy and rename the DLL_C folder and save it inside. Now let's set the simulation step to 10 nanoseconds and run it.
Great! It is working as expected. We have 2.5 volts at the output. Now let's create the interface for the digital controller with a DLL block. It will have one output, the PWM duty cycle, and two inputs, the output voltage and inductor current. Let's create the DLL by editing the C file in the buck model folder. Here we will just connect the inputs and outputs to the shared header structure. Write and read functions in this file are safe to interact with shared memory. Let's build the DLL by browsing to its folder with a command line. The make file inside it gives us the different options for building. We will select Plecs. Now the DLL is built, and we just have to link it in the schematic by setting the name in the block, and setting the same step as we did for the simulation. Let's now implement the digital controller. We will start by making a copy of the Eclipse project folder and renaming it as Digital Controller. We can import it directly in Eclipse and rename the project. Now it's time to write the application code that will control the buck converter.
Let's create a header file and write the application interface, like variables for input and output signals, and the functions to initialize and execute the periodic control task. In the application C file, we will define these variables and functions. And then create the data structures for implementing a simple PI controller with anti-windup.
Let's declare the control constants and needed variables. In the init function, we will initialize the set point to 3.3 volts and the control data.
In the task function, we will execute the PI step using the output voltage measurement and writing the PWM duty cycle.
Now that the application is ready, we will use the main file to integrate it with Nexus.
For that, we will be using slot 1. Remember that slot 0 is for the power model. Let the default time increment, and connect the variables to the shared memory as we did in the DLL. We will also add the init and task functions in the main loop.
Finally, let's build it.
Perfect! Our 2 units are now ready to be launched.
Let's edit the simulation config file and add the shared ID that we declared in the header. Let the default options for simulation timing. It will be synchronizing every microsecond, and just rename the units with a meaningful name. Let's start the simulation engine by typing KL Nexus, followed by the config file. They can now be launched in any order. Let's start running Plecs and opening the scope. Now let's launch our Eclipse project in debug mode.
We can set a breakpoint in the application init function, as well as in the task function. This one will be reached repetitively, and we can see how the PI is being calculated step by step, and the time of this unit is increasing according to the defined step.
Let's remove the breakpoint and let it run for a while. We can see a very slow response. Let's change the set point to 2.5 volts.
It is definitely very slow. Let's make it faster, multiplying both constants by 5. And again give the set point a value of 3.3 volts.
And back again to 2.5 volts. Great! It looks much better. In the next videos, we will incrementally show the features of the Nexus library.
If you liked this video, don't forget to subscribe and hit the like button.